presentation. Can you confirm that you can hear me? Okay. So good afternoon.
Oh, sorry. You can just put it in the full mode. Yeah, that's it. Thank you.
Good afternoon, everyone, and a very warm welcome also from my side to the first InPlasTwin webinar. My name is Janja Vidmar, and I work as a research associate at the Jozef Stefan Institute at the Department of Environmental Sciences, where I've been mostly focused on the analysis of inorganic nanoparticles and more recently also small microplastics and nanoplastics in environmental, biological, and food samples. And it's my pleasure today to introduce you to the InPlasTwin project, which is a newly launched coordination and support action project funded under the Horizon Europe program, and is designed to enhance expertise in the field of micro and nanoplastics analysis through a twinning approach. Running from October 24 to September 27, the project brings together 6 partners from 6 different countries, with the Jozef Stefan Institute serving as the coordinating institution. The main objective of the InPlasTwin project is to enhance the research and innovation capacity of the 2 project partners, Jozef Stefan Institute from Slovenia and the Agricultural University of Athens from Greece, in the field of micro and nanoplastics analysis. This will be achieved through collaboration, knowledge exchange, and networking with leading European institutions. And a long-term goal of this project is to deepen our understanding of the environmental and food-related impacts of micro and nanoplastics, with a particular emphasis on the agriculture. So, for this reason, a consortium of 6 partners was formed, already, as mentioned before, including Jozef Stefan Institute and Agricultural University of Athens. Those 2 partners will advance their knowledge in micro and nanoplastic analysis. AUA will also contribute its extensive knowledge in the greenhouse, crop cultivation, and investigation the impact of agricultural plastics on crop cultivation, while the 3 institutions, Flemish Institute for Technological Research from Belgium, Technical University of Denmark from Denmark, and Institute of Marine Research from Norway, will provide or are already providing cutting-edge expertise in micro and nanoplastics analysis through various advanced techniques. And they will also support capacity building by offering training, sharing their equipment, and guiding sample pretreatment and plastic additive analysis in the InPlasTwin project. And last but not least, the Foodscale Hub, a non-governmental organization from Serbia, is responsible in the InPlasTwin project for dissemination and communication activities to enlarge, of course, the project outcomes and raise the general awareness on the plastic pollution in the agri-food sector. So you can see that the consortium within the InPlasTwin project is a very multidisciplinary and covers different fields of natural sciences, analytical chemistry, agriculture, and also innovation management. So the InPlasTwin project has several specific objectives. First, it aims to foster long-term collaboration among project partners through a well-structured twinning activities. This includes short-term exchanges of both early career and also senior researchers, as well as hands-on and online training sessions, all focused on the knowledge transfer and transfer of best practices for investigating micro and nanoplastics. Secondly, the project also aims to strengthen the scientific and innovation capacity of participating institutions by building expertise in analytical techniques for micro and nanoplastics detection. And additionally, twinning activities also enhance the research profiles of the project partners, including improvement of their project management and administrative skills, as well as promoting diversity, inclusion, and ethical practices in the research. And finally, InPlasTwin also seeks to increase the social impact of the research related to the microplastic pollution in the agriculture. So all networking and sharing activities within our project are centered around a case study examining the uptake and impact of micro and nanoplastics resulting from the degradation of mulching films on strawberries. To just give you a bit of a context, so mulching films, whether conventional or biodegradable mulching films, are widely used in agriculture to primarily enhance the crop production. However, their improper disposal can lead to the accumulation of plastics residues in soil that can further degrade into micro and nanoplastics. They can persist in the environment, can affect the plant health, or even enter the food chain. And chemical additives in the plastics, of course, add to this risk. So given the limited research on the micro and nanoplastics release and impact on different types of crops, this case study serves as the foundation for the InPlasTwin research activities. So a series of laboratory and field experiments will be conducted within the project, and different advanced analytical techniques will be applied. First, we are currently studying the degradation of mulching films under realistic agriculture conditions. Then secondly, the sample preparation protocols are going to be optimized for the efficient extraction of micro and nanoplastics from environmental and food samples. Third, the project will also enhance knowledge and application of different analytical techniques for quantification, identification, and characterization of microplastics using different methods such as spectroscopy and mass spectrometry. And finally, also advanced mass spectrometry techniques will be used to analyze organic and inorganic plastic additives, including studying their leaching into the environment and food. All this knowledge gained will, through these activities, will be then applied in the controlled laboratory experiments, focusing on hydroponically grown strawberries exposed to micro and nanoplastics released from the degradation of mulching films. In addition to that, also a small-scale field experiment will be conducted on a commercial farm in Western Peloponnese in Greece, where strawberries will be cultivated using those mulching films. So finally, strawberry samples from both the lab and field experiment will be collected and analyzed for the presence of micro and nanoplastics and leachable plastic additives. Here, I will just give you a brief overview of the project progress, highlighting the main activities carried out during the first 6 months of the project. So the project officially launched with the kickoff meeting held in Slovenia last October. Then our partner from Agricultural University of Athens conducted site visits of strawberry fields in Western Peloponnese to prepare for the upcoming field experiments. Also, capacity building training was held at VITO, where JSI received hands-on training on project management. And our project was already presented at the 2 conferences, the European Winter Plasma Conference in Berlin and Agri-Food Plus Conference in Brussels. And last, but certainly not the least, also the researchers from the JSI and AUA participating in the first training activities at DTU, the Department of Environmental and Resource Engineering, under the guidance of Professor Dr. Nana Hartmann. The training focused on gaining hands-on experience in investigating the degradation, fragmentation and formation of micro and nanoplastics from mulching films under realistic environmental conditions. So here is just a brief overview of this experiment. So the training focused on 3 mulching films, 2 conventional and 1 biodegradable. And researchers use FTIR spectroscopy to analyze the chemical composition of those mulching films. The films were then pre-exposed to the UV light to simulate real-world conditions in the field. And a long-term degradation experiment was then set up with the films mixed into the agricultural soil samples. And this summer, the team, the InPlasTwin project team, will monitor the degradation process of those mulching films by assessing their weight loss, changes in the material properties, also visual and physical alteration, and ultimately also the formation of micro and nanoplastics particles will be followed. Also, the InPlasTwin is actively building synergies with other sister projects that are focused on microplastics research, such as the twinning project GREENLand, and today's webinar is also the reflection of these collaboration efforts. So at the end, I hope that this webinar will provide you with some valuable new insights into the topic of microplastics analysis in soil samples. I also warmly welcome all who recognizes the relevance of the InPlasTwin project to connect with us, exchange the knowledge and explore opportunities to collaborate. And I also encourage you to visit our website or follow us on social media to stay informed about our progress and activities. And thank you today for your time and attention.
Thank you, Janja, for your presentation. And now we can continue with our speakers. Our first speaker, as previously said, is Dr. Nataša Stojić from Educons University. Nataša, please, you can share your screen and
thank you, Courtney.
Give us your talk.
Can I ask you, because I already sent you my presentation, for you to share my presentation?
To share your, okay.
Please.
Sure.
Thank you.
You can see it now?
Yes, yes.
Just to put it in the full. Oh, why this? Start again.
Okay, shortly, while we are waiting for presentation, just to introduce myself, I'm a professor at the Faculty of Environmental Protection at Educons University. I work with analysis of organic and inorganic pollutants in the environment, and my research focuses on soil contamination, particularly the presence of microplastics, phthalates, heavy metals, and other persistent organic pollutants. I'm actively involved in national and international projects related to environmental protection, sustainability, climate change, and of course, I'm involved in the development of innovative monitoring methods and pilot systems for water and soil remediation. Shortly about Educons University. On the second slide is picture of our university. Educons University is a private university located in Sremska Kamenica near Novi Sad in Serbia. Our university has 7 faculties, including the Faculty of Environmental Protection. Also, we have 3 laboratories. One is a laboratory for environmental analysis. The other one is Abiotech Commercial Laboratory, and both support research, student training, and cooperation with industry also. But a few months ago, we also established the Center for Microplastics, and it is a dedicated hub for research and innovation in microplastic pollution. Our university has a lot of national and international projects, and right now we have 2 international projects related to microplastics. One is Interact project related to analysis of influence of agriculture on microplastic pollution. And another one is a Horizon Twinning project called GREENLand, which we can say aims to reduce microplastic pollution and promote a microplastic-free environment. We are leading partner on this project, and we have partners from Institute Alfred Wegener from Helgoland, from Germany, and researchers, our colleagues from University of Galway in Ireland. So as a part of this project, yes, we have also sister projects on our project, and one of these sister projects is InPlasTwin. And we are very happy to be here today with our colleagues from InPlasTwin and to talk about microplastic issues. So as a part of a GREENLand project, we developed, together with our partners, we developed precise methods for microplastic analysis and also gained valuable knowledge and experience in this field. So today we can share this expertise, this knowledge with other researchers and institutions that are just beginning to explore the issue of microplastics. So I will start with this presentation with sampling methods. I will not talk today about what is microplastics, what are sources of microplastics, and about influence of microplastic on human health. My idea was today to give you some information and some advices about sampling methods and some advices how to avoid contamination of your samples during analysis of microplastics. So sampling methods for microplastics in surface waters vary depending on the study goals, depending on particle size of interest and of course of environmental conditions. So three commonly used approaches are net sampling, pump-based sampling, and manual grab sampling. First one, we can use three types of nets. First one is manta nets, manta nets that are commonly used for collecting floating microplastics in surface water. These nets typically have mesh sizes ranging from 300 to 500 micrometers and are towed horizontally across the water surface. This method is effective for collecting larger microplastic particles, typically above 300 micrometers, and over large volumes of water in open water bodies. However, manta nets have some limitations. They are restricted to surface layers and tend to miss smaller microplastic particles, especially those below the mesh size. This technique is also not suitable for turbid or shallow waters and can be ineffective in environments with significant aquatic vegetation or debris, which can clog the net. Similar to manta nets are neostone nets. These nets are typically used for collecting also microplastics that are concentrated in the water's surface layer, including smaller particles than those captured by manta nets. And neostone nets also usually have mesh sizes ranging from 300 to 500 meters. For both, flow rate typically ranges from 1 to 3 cubic meters per minute, depending on the net size and towing speed. So the volume of water sampled can vary, but typically is from 1 to 10 cubic meters of water during a single tow. Bongo net is another useful tool in microplastic sampling, particularly for sampling the water column at various depths. It consists of two cylindrical nets that can be deployed at different depths, and this allows a more comprehensive collection of microplastics from both surface and subsurface waters. Bongo nets typically have finer mesh sizes ranging from 100 to 300 micrometers, and they are ideal for capturing smaller microplastics that may not be collected by manta and neostone nets. And the flow rate for bongo nets is typically from 0.5 to 2 cubic meters per minute, because they are designed for vertical sampling at various depths. So if we make comparison between these three types of nets, we can say that manta and nailstone nets are typically used for sampling surface waters and can collect large volumes of water in a short amount of time because of their larger size and faster towing speeds. And bongo nets are often used for collecting samples at various depths in the water column. With, I can say, lower flow rate compared to manta and nailstone nets because of their vertical sampling design. But the total volume of water sampled can vary significantly depending on factors such as the specific configuration of the net, the towing duration, and of course it depends on environmental conditions. The second method for water sampling is pump sampling. So pump-based systems offer a more versatile approach, enabling water collection at specific depths and across various water columns. These systems can be equipped with inline filters of varying mesh sizes, and they can include very fine filters down to 10 micrometers or maybe smaller. So this enables capturing or smaller microplastics that net methods might miss. This approach is especially valuable in studies aiming to characterize vertical distribution of microplastics or to target particle fractions. However, the complexity of this equipment introduces potential drawbacks. There is a risk of sample contamination from some internal plastic components of the pump system. But if we want to minimize this risk, then we need to always to have proper cleaning, to use inert materials like metal or glass materials, and to have rigorous blend controls, of course. Additionally, pump sampling can be logistically demanding in remote or undeveloped areas because of the need for power sources and for equipment transport, as you can see on this slide. And the next one is gram sampling, the third picture of previous slide. Manual grab sampling. Manual sampling involves the collection of water using glass or stainless steel containers. It is a cost-effective and simple method. And we can use it for sites with limited access or with low flow, such as streams, ponds, estuaries, and so on. Because it avoids plastic components, this method significantly reduces the risk of contamination. But the main limitation of manual sampling are the relatively small volume of water collected per sample and the associated need for high replication to ensure statistical validity. So in conclusion, we can say that each method has its strengths and limitations. In this table, you can see advantages and disadvantages of all three methods. But I can say that we can use a combination of techniques to get a full picture of microplastic pollution across different size classes and water depths. So we can choose our sampling methods based on our study goals, on particle size we are targeting, how accessible the site is, and of course, about resources that we have available. Next is soil sampling. Soil sampling for microplastics also requires careful methodological planning if you want to have a representative sample to minimize contamination and to capture a wide range of particle sizes. So the choice of tools, sampling depth, sample handling, and all of that play critical roles in the accuracy and reliability of these results. Sampling tools, of course, it is very important material that they are made of. So we always recommend using stainless steel or aluminum tools to avoid introducing plastic contaminants. The focus is often on the upper layers of the soil profile, generally within the top from 5 to 20 centimeters, where microplastics tend to accumulate. In sites affected by specific sources, commonly we use vertical profiling, and this method involves collecting soil samples at various depths to assess, of course, the vertical distribution of microparticles. Given the special heterogeneity of microplastic distribution in soil, we prefer composite sampling. This involves collecting multiple sub-samples from across defined sampling area and truly mixing them to create a single representative sample. Composite sampling helps reduce local variability and provides a more accurate picture of the average microplastic concentration across the site, and the amount of composite sample typically ranges from 1 to 4 kilograms, and it depends on the site characteristics, and of course it depends on pollution sources. So this method is especially useful in areas with mixed pollution sources like city parks, farms, or if you are sampling near some land. So to ensure the integrity of the sample and to avoid contamination during soil sampling, it is essential to follow strict protocols. On next slide, we have some advices for you how to avoid contamination during field procedures. First of all, we recommend to avoid synthetic clothing. Operators should wear laboratory coats made of 100% cotton, and also we recommend cotton gloves and head coverings. Next advice is to use inert sampling tools like stainless steel, glass, aluminum equipment, and wherever is possible, we should replace all plastic tools. All equipment must be thoroughly cleaned using filtered distilled water and wrapped in aluminum foil prior to field use. Sampling should be carried out in sheltered conditions or with the wind of the operator's back to reduce airborne fiber contamination. Containers used to store samples must be pre-rinsed with filtered water. And as I said, plastic containers should be avoided. Our advice is always to use field blanks. These are essential in detecting contamination introduced during sampling, but we will talk about this a little bit later. And of course, to avoid plastic tape or plastic labeling, because this can easily shed particles, label should be printed on or written on waterproof paper and sealed with foil if needed. On the second slide, we can see laboratory procedures. In the lab, control of contamination becomes even more critical, especially when processing low concentration samples. So common lab contaminants include microfibers from lab coats. Then it should be dust can be the dust from ventilation systems, residues on bench tops, and of course contamination from lab water or other chemicals that are used in process of microplastic analysis. So some advices are to have dedicated clean spaces. Ideally, microplastic sample processing should take place in a clean room, in a clean laboratory, or at minimum in a laminar flow hood equipped with HEPA filters. All water and chemical reagents must be passed through membrane filters with pore size from 0.2 to 0.7 micrometers before use, and these steps alone can prevent a major source of particle contamination in laboratory. Wherever is possible, we need to use glass or metal equipment. Then all working surfaces must be whipped regularly with ethanol soaked lint-free cloths. Tools should be rinsed between samples with filtered ethanol or water and whipped with aluminum foil. We should use protective clothing. Use of laboratory clothes made of natural fibers is always recommended, and laboratory staff should avoid using personal care products like lotions, sprays, and something similar that could contain polymers. We should cover workstations. We should keep all equipment and sample containers covered with foil or glass petri dishes whenever they are not in use. And also we regularly should check air quality. But about this we will talk in the next chapter about where I'm talking about quality control. In addition to preventive measures, all researchers dealing with microplastic must include a suite of quality assurance and quality control tools in order to detect, to quantify, and correct for procedural contamination. The goal is not only to minimize contamination, but to ensure that any introduced particles can be accounted for and excluded from final data analysis. So we have 4 types of blanks that we must take care about it. So the first one is field blank. A field blank is prepared in the lab with a clean matrix, but is taken into the field and handled exactly like a real environmental sample, except it never actually comes into contact with soil or water. It is opened, exposed, stored, and transported in the same way as actual sample. What it tells us, field blanks help reveal contamination introduced during sampling, whether from tools, containers, protective gear, or ambient environmental sources like, for example, dust or air. And why it matters? It's a powerful way to distinguish between what's actually in the environment and what might have been introduced during the sampling process. The next one is a negative blank. Negative blank is used to check whether contamination is present before any sample is processed. It typically contains just a clean solvent like ultra-pure water or a clean matrix such as filter. This blank is not processed through the entire analytical method. It simply acts as a starting point to make sure all the materials like containers, reagents, lab air, and so on are clean. What it tells us, if contaminants are detected in negative blank, it means something in the laboratory environment, such as the air, glassware, or chemicals, may be introducing impurities. And why it matters? It shows how clean the laboratory environment is before the sample touches anything. The next one is laboratory blank, also known as a method blank. And this laboratory blank is processed actually like a real sample, but it doesn't contain any actual environmental material. Instead, it contains just the clean solvent or matrix and goes through all laboratory preparation and analysis steps, including extraction, filtration, digestion, and instrumentation. What it tells us, any contamination detected in a laboratory blank is likely from reagents, from instruments, filters, or even from analyst handling. And this is matter because it ensures that the lab procedures themselves are not contributing to false positive or elevated values of actual samples. And the last one is a positive blank, also known as a recovery control. Recovery control contains a known amount of one or more polymers added to a clean matrix. This blank is prepared alongside the real samples to verify that analytical method can detect and accurately measure the analyte. It shows whether the method is working correctly, If the analyte is not fully recovered, it may indicate problems with the extraction or some detection steps. This blank is crucial for assessing accuracy, precision, and recovery efficiency, which are, of course, key indicators of method performance. After this, I will give you short advice about, also as a part of quality control. You should record detailed metadata for each sampling and processing event, like personnel and clothing, materials of clothes, then information about equipment and cleaning protocols that you have used on field and in laboratory. You need information about weather and environmental conditions, about sample handling and storage details, and results of each blank or control. This clarity helps us understanding the data to compare results between studies and is needed for creating standard monitoring methods. So the last slide, we have some key takeaways from this presentation. I can conclude that contamination control in microplastic studies is not a secondary consideration, but rather a primary determinant of data quality. By applying strict protocols in the field and laboratory, and by including appropriate blanks and controls, researchers can significantly enhance the credibility and reproducibility of their findings. So, efforts should be made to standardize methodologies, to share best practice across research groups, and to implement robust quality control rules. So only then we can trust the environmental data and make decisions about potential risks posed by microplastics to ecosystems and human health. On the last slide, I want to thank you for your attention, and I want to ask you to scan QR code, and you will on that way enter on the site of our conference. I want to invite you to our conference that will be held in November in Novi Sad. Our conference is about microplastic in organic rich matrices. So we will have great key speakers, and it will be our pleasure to be your hosts. Thank you very much.
Thank you, Nataša, for your talk, which really showed us the knowledge transfer that you had during your GREENLand project activities. It's really something that each person that now listened to your presentation, something that can be repeatable and understandable. So I'm very happy that we had you as a speaker today. I invite all participants to activate participate in the Q&A session afterwards and to connect among each other. After Nataša, we will now have opportunity to hear experience from her master student Galina Ćurčić. Galina, please give us a talk about your experience that you had at Alfred Wegener Institute.
Thank you so much. So as you heard, my name is Galina, and I am a recently graduated Master of Analytical Chemistry in Environmental Protection. And so I'm very excited to tell you about the work that we did during my 2-month stay at the Alfred Wegener Institute at Helgoland, which was a part of the GREENLand project and also part of the research work for my master thesis. So I guess the primary goal of this visit was to try out all different protocols that we found in literature that were describing different methods for extraction of microplastic from soil samples, and then compare them and just sort of Frankenstein together one optimal protocol, which we would then use in the future. And when I say optimal, I mean a protocol that would allow us to extract with a high enough recovery rate all kinds of microplastics down to 11 micrometers in size, but they would at the same time take the least amount of time possible, and also they would have the lowest costs and environmental risks. So with that in mind, we started our testing actually with, excuse me, I'm not in, okay, there we go. With the protocol that was suggested for us by our partners from Galway University. And what they said is that we should start our extraction with organic matter digestion using hydrogen peroxide directly on our soil samples. And you will see shortly that this reaction did not go to plan. This was a very strong reaction, which resulted in a lot of heat being released, and also a lot of bubblage and foam formation. We were really concerned about the heat because we were thinking that perhaps our microplastic particles would get melted. And we were also concerned about sample loss due to the foaming and like the physical leaving of the sample. So to kind of circumvent this, we tried to cool down our samples using an ice bath. And at first it seemed to work. However, after removing our samples from the ice bath during the incubation period, the foam started forming again, and we lost a lot of sample again. Additionally, during the weekend, one of our first tests actually sprouted, and this left us truly wondering if we even managed to digest any organic matter at all. So for all these reasons combined, we chose to abandon this approach completely. And we realized that we probably should not start organic matter digestion before we cut down actually on the amount of sample that we have to digest. So we decided that we're going to take a different approach, and we're going to start with a density separation just to kind of eliminate most of the sample that we don't actually need. So we started preparing, I guess, our solution for density separation. And at that point, we chose sodium bromide as the salt that will be used. Now, we chose this salt. There's many alternatives that could have been used, but we chose this one because it has a good balance, meaning that it has a high enough density that could be achieved, but it has a low enough cost and a low enough environmental impact. So that's why we chose sodium bromide. And then we started testing it with a centrifuge density separation. This is a very simple protocol, which just involves you sort of mixing your sample with the solution very well, and then using a centrifuge to separate the soil and the solution, after which you just suck up the solution using a glass syringe. Now, this is a very short protocol. However, after repeating this for 6 times, we still had leftover microplastics in our sample. And at that point, we realized that from a short and simple protocol, we were getting a very complex one if we wanted to extract truly most of the microplastics present. So for that reason, we decided that this would not be something that's optimal to use. Instead, we opted for an overflow density separation. And this is a procedure that does last longer on its own because it takes more time for the soil to settle on its own when not using a centrifuge. But after 3 iterations of this protocol, we were very satisfied with the amount of microplastics that were released, and we decided that that was enough to continue with our extraction protocol. So in that way, we actually cut down on time by using I guess, longer procedure. So we ended up with this kind of stainless steel filter at the end. And on that one filter, we tried to concentrate 3 separate density separation particles. And so you can see that now we have just this filter that has way less material on it, and we have significantly reduced the material that needs to be organic, that needs to be digested. So at that point, we decided it's a good time to try organic matter digestion again. But this time around, we tried to use Phan's reagent, and this reaction went very well, and the sample actually behaved in a manner that we expected. And you can see how the filter looked like afterwards. I'm going to go back again so that you can see this was before the Phan and this was after. And I think the efficiency is pretty obvious. But what is also obvious is that we still have a lot of these grass-like big particles present, and they are a big problem in the future. So we needed to take care of them somehow. Considering that we now have a lot less, I guess, particles on our filters, we decided to use a 500 micron kitchen sieve and basically separate a larger fraction from a smaller fraction in this way. The larger fraction was then visually inspected for larger microplastic particles, and the smaller fraction was further purified. Now, I would like to mention at this point, we did have access to enzymes, and enzymes could have helped us actually remove these, I guess, grassy and woody particles. But considering that we were trying to make a cost and time efficient method, we were really trying to circumvent using the enzymes. So because they are very costly, because working with them is tricky and it takes a long time for the reactions to actually finish, we really wanted to push, I guess, without them for as much as we could and see if we could get the protocol to be good enough to be used without the enzymes. So that is why we used a kitchen sieve at this moment. And when we finished with the kitchen sieve, we did have a much better situation. However, as you can see on this filter already, there is a lot of dust particles that are still left and that would clog up our anodiscs if we proceeded to anodisc filtration at this moment. That's why we decided that we need another purifying step, and we went for a secondary density separation, this time using a separation funnel. And as you can see on the pictures, the separation was pretty efficient. However, due to the very efficient separation, our funnels actually clogged, and we needed to use wires to let the dust through the funnel. But that was a minor setback, and this was a really efficient step. And with that, we cut the number of particles significantly, and we had something that was manageable for anodisc filtration. So we proceeded to that step. And approximately speaking, having in mind that every sample of soil is behaving in a different way, you could have around 5 anodiscs from each sample, which, if you're using the microFTIR, we were using Lumos, is around 2 days of scanning. So that is what we ended up with per sample. At that moment, when we had an idea of what our protocol will finally look like, we needed to do a recovery test. And for that, I counted out a number of these pristine, standardized spheres. I think they were polypropylene. They were around 150 to 180 micrometers. And I put them in our soil samples that were weighed. And then I proceeded to do the entire procedure with them inside. And afterwards, at the very end, I counted them up again on the anodiscs, making sure to only count the ones that were still in their original shape and not count the ones that were fragmented. And with that in mind, our recovery was over 95%, which means that less than 5% particles were lost or fragmented, which is very nice, but we have to keep in mind that this was done with standardized microplastics and does not fully translate to the environmentally present, environmentally weathered microplastics, which we would have had in the soil. But simply we needed a sort of reference point, so this was the only way that we could do it, and this showed a nice result, but it is most likely not completely the same for the environmentally present microplastics. So in conclusion, our protocol consisted of sampling, right, drying our soil and very lightly homogenizing it and getting 10 grams into a straight net bottle. Then we would proceed with overflow density separation 3 times in a row, condensing everything onto one disk, which would then be exposed to Fenton's reagent. And after the reaction, we would apply a kitchen sieve to divide our sample into a smaller and a larger fraction. Smaller fraction would be further purified in a separation funnel. And finally, we would have the particles, which are going to anode disk filtration and micro FTAR scanning. With that, we sort of finished, I guess, our task, and we formulated an quote-unquote optimal protocol for us. This protocol was formulated using the laboratory equipment that was already present and should be present in most laboratories that are dealing already with microplastics in water or sediment. So for that reason, it takes no further costs, I guess, to start implementing this protocol. We try to keep the time at a minimum, as well as the environmental impact and, of course, human health risks. Now, we are very well aware that this protocol could be further optimized and improved upon. And for starters, I would really like to test the efficiency of enzymes, and if maybe they are just so good that it's justified to use them, because we cut down on a lot of anode disks and we shorten the scan time. I would also like to test if 10 grams of sample is even representative enough of the entire sample that we collect. And at the end, of course, we would have to do a series of interlaboratory comparison to truly see if we are able to gain similar enough results using this protocol in different laboratories with the same samples. And with that, I would like to thank you for your attention. And I would like to thank our project partners, Dr. Sebastian Primke and Dr. Phan, as well as the rest of their team, because they kept up with my soil shenanigans for 2 months. And I would be happy to answer all your questions during the discussion period.
Galina, thank you very much. Your smile really says everything. So beside the knowledge that you gained, you really gained a really nice hands-on experience during your visit, and you gave us presentation in so much detail, and I hope that other colleagues that are participating can further communicate with you, because I know how it is hard to establish a good protocol for microplastic extraction. So after Galina's talk, I would now give the floor to our InPlasTwin project partner, new Phan from VITO Institute. New Phan, please share your presentation and learn us more about your experience.
So, hi everyone, can you see my slide now?
Yes, it's okay.
Cool. Okay. Yeah, so my name is Phan, and I'm currently a postdoc researcher at the Specialized Organic and Inorganic Analysis Laboratory at VITO. And today I'm going to share with you my experience with micro and nanoplastic analysis in soil. So just a bit about my background. So I did my PhD at Lancaster University, where I involved in a Horizon 2020 Stop-Blast ITN project, which is a EU-funded project with 14 universities working together, and we look at macro and microplastic in agricultural soil system. And in this big Stop-Blast consortium, we look at detection of plastic in soil, to understand the input of plastic, and also the degradation pathway of microplastic in soil, and also transport and impact of plastic in soil. And my PhD were focusing mainly on the detection of plastic in soil. So today I'm gonna share with you my experience and insight in this aspect. So first this is the content of my talk. First, I will quickly talk about sampling soil for micro and nanoplastic analysis, and later extraction of micro nanoplastic and analytical method and some case studies, and finally is the summary. So how to sample soil for microplastic analysis? Unlike, for example, water sample, where we already have a better standardized product procedure for sampling, for soil is a bit tricky and there's not standardized method yet. And imagine when we go into the field and we have to really think about where to sample and how to take the representative sample. That is a really tricky question. And for soil sample, so we have different strategy. For example, we can do simple like random. We can collect random sample on the field, or we can do stratify randomly, or systematic sampling, where we do like a risk scale, where we do sampling. And the important thing is to take representative volume, like how much amount of soil or how much sampling volume should we take to obtain representative sample. And it's really depend on the concentration of the plastic that we have in the field. For example, with lower concentration, we need to take more soil sample, like more higher volume of soil to obtain representative sampling. And with field that have higher concentration, we need to take lower concentration, like lower amount of soil and also lower number of sample. So for example, this is just a study that I really like, where they do a simulation on like the expected concentration of plastic and the required number of soil sample that we should take. And it clearly from this graph that the higher concentration, the less amount of sample we should take, for example. And also from this study, they recommend that it's better to use larger sample, for example, a 1 meter multi 1 meter quadrat, instead of taking multiple cores of soil samples. So taken this into account when we do sampling, we first know about the history of the field. For example, is it a highly contaminated field, or is it low contaminated, like remote area? We will need to take more sample. And for example, for one of our study, we have an estimated like concentration for the background soil where there is not a lot of contamination, and we decided to take a large soil volume. For example, here is a 50 centimeter multi 50 centimeter quadrat, and then we do like homogenization in the field. And here we take 20 centimeter deep soil, so we dig the soil in until 20 centimeter, and we harmonize with stainless steel scoop. And it's also important to do some sort of soil characterization, because it's really affect our microplastic analysis. For example, bulk density is necessary because we can also transfer from mass to volume of like the unit, for example, number of particle per gram or number of particle per meter square. And also some other soil characterization that really affect with the analysis. For example, like texture, like the amount of clay, the amount of sand, and the amount of loamy in soil can affect the result. And also the organic carbon, that is clearly a positive for the analysis. So for this, we characterize with like particle size analysis for texture analysis, and loss on ignition for organic carbon. So this is a quick overview of how we do sampling and also how we do soil characterization. And after that, after we have our representative soil sample, we will go to extract. So currently there are a lot of protocols to extract microplastic from soil, and it's really important to know that the way we choose our extraction procedure is really depend on our target analysis and also the endpoint method that we use. For microplastic, the common procedure would be start with first with density separation, filtration, and then organic digestion. For density separation, we have several setup available here, and depending on, for example, the amount of soil, the type of plastic size that we want to analyze, we can use different setup here. For example, this sediment microplastic isolation unit is allow us to use a high volume of soil, and it's really simple and easy to use. However, because it's made of PVC, which is plastic, so we can also cause cross contamination, and it make the limit of detection of the method higher. So if we want to measure something very low concentration, it might not be the best approach. And similar for separation funnel, we can do with lower amount of soil, like less than 10 grams, for example, and it's also efficient. But for sandy sample, where we have a lot of sand particle, the sand can clog with the valve here, and this is not good. So it's only good for those very fine samples and very small amount. And also we have overflow that somewhat that we mentioned before, and also the free thaw approach. This approach is also really good when we and very easy to handle, but again, it can only work for a small amount of soil, like 10 to 20 grams of soil. And the amount of soil that we need to analyze also depending on the limit of detection of our method, and also how contaminated the soil. For example, if soil is highly contaminated, we only need to use a small amount. But if the soil is not really, like from a remote area, we need to use larger amount of soil. So this is also something we need to consider. And for density medium, we can use several solutions. Some can use even only water, but that only allow us to analyze very light plastic. And if we want to measure something with higher density, for example, tile wear particle, which has density from 1.6 to even 1.2 to even 2.2, then we need to use very heavy brine solution like zinc chloride or sodium polystungstate. So again, the selection of setup and then the solution to do density separation really depend on our target analysis. And then filtration, normally we use stainless steel mask, and depending on what size we want to measure, we can use 6 micron, 20 micron, or above that. And after that, we do organic digestion. So currently, the most straightforward procedure will be Phan digestions. In some of our sample, we also do enzyme digestion, which include, for example, cellulose, lipase, and amylase. And however, the enzymatic digestion is expensive and is also lengthy. So for us, the optimal one would be still Phan digestion. And again, depend on the amount of for example, sand particle or the amount of organic matter in our soil sample, we can repeat it, the density separation step, or we can repeat it, the organic digestion step. Some sample we do 1 or 2, even 2 times of Phan digestion, and for some sample we do more two-step density separation. And again, this procedure we can decide after we have a full characterization of soil. Our soil, for example, how much clay, how much sand, and how much organic matter we have in the soil. And after we have the potential microplastic on a filter, we then do measurement of plastic. And at the moment, we already we have tested this method for micro and nanoplastic analysis. And again, the selection of the analytical method should align with your specific research objective. For example, if we want to know the information about particle, which is really important for someone who is interested in toxicology study, to know the impact, the health impact, the transportation of plastic, then we can use micro FTIR or micro Raman, or we can also use now red standing fluorescent microscopy, which is a quick approach. However, this method gives us quite a high level of false positive from especially for soil sample with a lot of organic matter. Micro Raman can allow us to measure particle down to 1 micrometer. However, we also have a lot of interference from the organic matter. And with FTIR, our current protocol allows the analysis down to 11 micrometer, and it is much easier to use compared to Raman, and more straightforward. But the disadvantage is the size limit, that we can only go to until 11 micrometer. And for mass analysis, we have pyrolysis GCMS. We also have NMR. We did use this for mainly the monitoring of biodegradable biodegradation of the biodegradable plastic, which I will. But this one is require a special extraction, that we use solvent extraction. So only the plastic that dissolve in the solvent, in the specific solvent, can be used with this method. For example, biodegradable PBAT, PLA dissolve in chloroform and methanol, and also polystyrene, for example. And for very, very low concentrated sample, we have the very sensitive thermodisruption proton transfer reaction mass spectrometry that allow us to measure down to nanogram level. So this method we use for example, plastic from the remote Antarctica samples. I will also give a case study for this later. So it's clearly that we have different protocols and different analytical methods available. So for microplastic, and for nanoplastic, there is not yet a lot of study on the extraction of nanoplastic from soil. So here we did try to develop a method for nanoplastic from soil. Start first with organic digestion of the soil sample. I mentioned again because we will be using a very sensitive method here. So we just need a very small amount of soil. Here we use 3 grams of soil, and we do organic digestion with hydrogen peroxide. And then after that, we filter our sample, or we use low pressure evaluation if we want to go down to really below 1 nanometer of that size. And then we apply thermodisruption, and then for subsequent analysis with TD-PTMS. And for particle, we also try the correlative SEM Raman, which theoretically allow us to measure down to 500 nanometer. But because the soil matrix was so difficult because of the organic matter, so the acquisition of the Raman structure for the nanometer particle was not really successful. So we only successful with the TD-PTMS approach. So as I already mentioned with you, a lot of analytical method available and a lot of protocols. So part of a PhD project that I did was the aim was to compare different approach for microplastic analysis. And this is a collaboration between Wesleyan company in Germany, the university that I did my PhD, Lancaster University, Wageningen in ETH, and University of Bonn in Germany. And in this experiment, we test different methods for the analysis of different plastic. For example, biodegradable plastic from mulching film, conventional LDPE, polystyrene, polypropylene, PET, PVC, like all the very popular plastic. And we have different size range, like the large plastic and the very small plastic down to 20 micrometer. And with this, we also test how the method work for different type of soil, because they can have different level of interference. So we test 3 types soil: loamy, sandy, and clayey. We had different organic and clay content. And we have several protocols and several procedures tailored to different protocol. For example, digital microscopy, which is really cheap, easy to use. And then fluorescent microscopy, FTIR, Raman, pyrolysis GCMS, and also NMR, but only for the biodegradable plastic from the mulching film. And for the result, we find that for the bigger plastic, which is from 500 to 1 millimeter, the recovery is pretty high, above 80% for almost all method. And for example, for the fluorescent microscopy, we can see that the fluorescent intensity vary depending on the plastic type. And for the biodegradable plastic, this method is not a good one, because the plastic didn't fluoresce with Nile red, and we have to at the end use the bright field mode to quantify this plastic instead. And for the smaller plastic, the recovery really change depending on the different method that we use. So here, for the smaller plastic, we test the conventional LDPE and the biodegradable plastic mulching film, and that is from 20 to 250 micrometer in size. And we see that, for example, for the conventional bright LDPE particles, and the fluorescent approach seem to be the more effective compared to FTIR and Raman, because the small particle, the fluorescent is sensitive to small particles, like it can go down to 3 micrometer with our current setup. And for FTIR and Raman, FTIR is limited to 11 micron, so we somehow can miss those small particles. And similar with Raman, with the automatic scanning approach, we can also miss some particles. And also, of course, we lost small particle during our procedure, during the extraction procedure. And we can also observe that the biodegradable mulching film is more difficult to measure compared to the conventional. Which could be due to the very strong organic digestion that we use, that can somehow degrade the plastic, that lead to the low recovery. And the best approach currently for biodegradable plastic is the NMR approach, which use solvent extraction. So and it gives us about 90% of recovery for this type of plastic. And we also observe that the different type of soil really affect the analysis. For example, here we see that the clayey soil, the blue color columns, is have lower recovery compared to the other soil like sandy or loamy. Our explanation for the moment is that those very tiny clay particle, and when we use it with a high salt solution, high concentration of salt solution of zinc chloride, it can cause some sort of irrigation due to electrostatic interaction. And during this sort of irrigation, we lost our small particle because they settle down during the extraction, during the density separation step. And also the clayey soil have also high organic matter content. You can see the small gray figure here, and it really interfere and make the analysis difficult. For example, organic matter, when we do Raman analysis, it can cause fluorescent signal, and it's really hinder the Raman signal of the plastic. And so that is one experiment that we did. This study already been published, and you can also find it online. Next, we also wanted to test different approach, like the fluorescent microscopy, the infrared, and the Raman spectroscopy for particle analysis. What we did is that we do the analysis of using 3 different approaches on the same sample, and it's really interesting for us to find out that some plastic, they can be identified only with fluorescent microscope, and some can only be identified with Raman or FTIR, and like some. So for example, here in the figure A, you can see that like this particle is being identified with fluorescent, and it can also be identified with FTIR, and so we have a good overlay, so it is good. However, in the figure B, we have some plastic it's been detected with the fluorescent. It gives very beautiful fluorescent images, but it cannot be detected by FTIR, which could be due to the thickness of the particle and all the very thin fibers that go below the resolution of the infrared light. And also we have some case where we detected plastic with FTIR but not the fluorescent microscopy. So you see here in the figure D, this polyethylene fiber, they was detected with FTIR, but in the fluorescent microscopy approach, it fluoresces really, really weak, that if we do not really try to enhance our lasers, it will not be clearly detected. So this image has been already enhanced the brightness. And fibers is a really tricky microplastic to work with. Here we have those fibers that cannot be detected by both FTIR and fluorescent microscopy approach. So this result is showing us that all of these methods that we have, fluorescent, FTIR, and Raman, they all have false positive, false negative, meaning that they cannot measure some of the plastic. Not to mention that they also have false positive come from the organic matter, especially from the soil matrix. So this is just an overview of like the different plastic concentration obtained from different methods. Like for total microplastic, the fluorescent microscopy seems to give a higher concentration, though not statistically significant. Could be due to the false positive of this approach, and similar with the particles. And for the fibers, we also see here that fluorescent tend to give higher concentration compared to FTIR and Raman. However, at the moment, my experience is that the Raman give more reliable like manual Raman give more reliable analysis for fiber because we can really focus on them and can really measure those very tiny and tricky fibers. So I was just quickly going through the protocols and different analytical method that we use, and and now I will show you some case studies that we use to understand the agricultural pathway of microplastic into soil. So we look at microplastic in agricultural products like seaweed sludge or anaerobic digester from animal manure, and we collect soil sample that receive this sort of fertilizer, and we see how these fertilizer contaminate soil with plastic. So what makes our study special is that we we try to measure down to to smaller particle than the current literature. We go down to 25 micrometer, and we obtain more representative sampling method by using a bigger size of the soil volume, like I mentioned earlier, and we apply several protocols like fluorescent, Raman, and FTIR, and we also pay really detail into QA/QC procedure, including using procedure blanks and method recovery by using the arrogate standard, using the cospheric sphere, the fluorescent cospheric polyethylene particles. So this is just an example of our result. So we found several type of plastic in our seaweed sludge sample, with mainly from with polyethylene, polyester, polypropylene, and with the FTIR approach, we have also the size distribution of the plastic in the sample, and also the shape distribution, the shape like elongated and particles, and similarly, we measure the plastic in our soil sample that received seaweed sludge, and we found that the soil that received seaweed sludge, which is in gray bar, have much higher concentration compared to the soil that do not receive seaweed sludge, or the non-agriculture soil, which is in red and in blue bars. And we also find that the plastic profile of the seaweed sludge amended soil represent quite closely to the plastic profile of the seaweed sludge, and some plastic like polyacrylic or polyacrylic, polyester, and acrylic come from the sludge, but they do not present in the non-agriculture or the no apply seaweed sludge field. So it's a clear evidence of the contamination of seaweed sludge to soil with microplastic. And also another case study, when we look into very, very remote soil sample, we take soil sample from the inland Antarctica and unclide the seaweed sludge sample, the soil that treated with seaweed sludge, which is highly contaminated. These soil are more tricky because they are really, really lowly contaminated. So we have to develop several different methods. So how to really reduce our limit of detection so that we can really detect our plastic. And so we develop both microplastic extraction and nanoplastic extraction with this protocol, like for microplastic overflow, phantom digestion, and then using fluorescent microscopy. And for nanoplastic, is the protocol that I described earlier with digestion and then filtration, and then go to TD-PTMS. And for the result, we find that only one sample of the soil sample in Antarctica have microplastic that is above our limit of detection. And this is some shape of the plastic that we found in the sample. And for nanoplastic, we found them across almost all of our samples, and we found the plastic like tire-wear particle, polystyrene, polyvinyl chloride, polyester. And it's also interesting that we also found nanoplastic in even deep soil sample, like below 40 centimeter, meaning that these plastic can also filtrate vertically into the deeper soil layer. And with collaboration, we also do sort of plastic modeling to understand where the nanoplastic come from, and we find that it's really depend on the seasonal. For example, in the Antarctica summer, the source is mainly from local source, which could contribute from scientific activity in this area, whereas in the Antarctica winter, it was from atmospheric deposition from New Zealand, from South Africa, that bring the nanoplastic here. So those are just the case study that I have done, and just a quick summary of like here we found that plastic pollution is widespread. We found them everywhere from inland region to even remote area, and agriculture is a significant source, but atmospheric transport should also be considered. And we also see that there are various methods available for micro and nanoplastic analysis. So the important why we have not yet have a standardized procedure. QA/QC is really important. We need to report limit detection and method recovery. And we also, for interlab comparison, is really important that hopefully in the future we have standardized reference material that can help us to move to a more standardized method for micro and nanoplastic analysis. Yeah, so that the end of my presentation. Thank you very much for listening.
Dear Nyufa, really thank you for sharing with us all experience that you have in microplastic research. I'm happy that we heard not only about microplastic research, but you tackled the really highlighted point about nanoplastic research, which is now also emergent contaminant in the environment. According to all your presentations, we really can conclude that we passed all the way from the extraction and from the sampling to the protocols, extractions, and methods used to detect microplastic and nanoplastic. But the question that arises is now also in the chat, which I was thinking also to ask, is actually what to do, how to deal with microplastic in the environment. So Quynh asked, has anyone done research on using microalgae for microplastic degradation? So I invite our speakers or maybe our participants to give their view on this question.
Maybe I can start first. Me, myself, I have not used microalgae for microplastic degradation. But so you mean like to remove plastic, like to degrade the plastic? No, but I think there has been some sort of because we can use some sort of enzyme that come from this mushroom or microalgae, and I think there has been some interesting research extracting those sort of enzyme or using those mushroom or algae to degrade plastic. So I think there has been literature on that, but I'm not specialized in this.
I have to say that Quynh actually raised interesting question, which gave me idea for our next maybe webinar topic, that we can think about inviting speakers from this field and organize a webinar on this topic. Thank you, Quynh, for raising this issue. I know that we are a little bit out of time, and I would like to ask you if you have time for more questions, or should we conclude this webinar? Speakers are now here. I see them. I have to say that maybe one question from my side would be, can you give us your opinion on using actually weathered plastic instead of lab-made microplastic standards for spiking in method validation? Have you had some experience working with either type of these two plastics in your research?
Me myself, for the testing of the method, we haven't used those like weather plastic yet, but there are also several ways, and this is also what I wanted to explore during my postdoc. For example, like using UV degraded plastic, or the plastic that we collected from the environment, like for example that has been contaminated with biofilm, with more organic matter like oil from the soil, for example, and also the plastic that has been physically degraded or UV degraded, and then we can cryomill, like grind them into smaller pieces and use as a test material. Yeah, so I think that's a valid point, and yeah, that's what we will for sure try in the future.
Thank you, Nyufa.
From our point of sight, we have experience with recovery, as Galina said, but unfortunately we used also standardized microplastic, pristine microplastic, and it is better to use weather plastic. As Galina said, she counted about 170 particles. And we had a great recovery, but as she mentioned, it is not quite a reliable result because weather plastic behavior is quite different than this one. So next step, I hope that we will have chance to use weather plastic, and we will have, I hope, the same results. Maybe not the same, but because we have a great method for extraction of microparticles from organic rich soil, I hope that we will have pretty same recovery.
I would be way happier if I could use actual weathered plastic and different kinds of it, right? Not just one polymer type, but like all sorts and all kinds and all shapes. I think that would matter much more. Those kind of results would have much more of a significance than these right now.
Thank you, Galina and Nataša, for your answers, and Njufa as well. Once again, I would like to ask our public and participants, would you like to ask our speakers something? So if there are no more questions, I would like to thank you once again for attending this webinar. I would like to thank our speakers for really insightful presentation. And I would like to call all of you for collaborations, because there are a lot of issues still really not known in this field of microplastic research. And I assume that knowledge exchange is now something that all scientists need to establish protocols and procedures, especially for the detection of microplastics in soil. We invite you to follow our projects on our social media and to stay updated on the future webinars that we will organize. Thank you once again, and I wish you a pleasant rest of the day.
Thank you very much.
Thank you.